by which the center of gravity is at the lowest point when the image is standing upright. And we may be certain, when I am tilting it over C56, that I am lifting up the center of gravity, point A, and raising it from the Earth. All this is effected by putting a piece of lead inside the lower part of the image and making the base of large curvature. And there you have the whole secret. But what will happen if I try to make the figure stand upon a sharp point? You observe, I must get that point exactly under the center of gravity, or it will fall over, thus endeavoring unsuccessfully to balance it. And this, you see, is a difficult matter. I cannot make it stand still. But if I embarrass this poor old lady with a world of trouble and hang this wire with bullets at each end about her neck, 57, it is very evident that, owing to there being these balls of lead hanging down on either side, in addition to the lead inside, I have lowered the center of gravity, and now she will stand upon this point, 57. And what is more, she proves the truth of our philosophy by standing sideways. I remember an experiment which puzzled me very much when I was a boy. I read it in a conjuring book, and this was how the problem was put to us. How, as the book said, how to hang a pail of water by means of a stick upon the side of a table. Figure 8. Now, I have here a table, a piece of stick, and a pail, and the proposition is, how can that pail be hung to the edge of this table? It is to be done, and can you at all anticipate what arrangement I shall make to enable me to succeed? Why, this. I take a stick and put it in the pail between the bottom and the horizontal piece of wood, and thus give it a stiff handle, and there it is, and what is more, the more water I pour into the pail, the better it will hang. It is very true. Before I quite succeeded, I had the misfortune to push the bottoms of several pails out. But here it is, hanging firmly, figure 9. And you now see how you can hang up the pail in the way which the conjuring books require. Again, if you are really so inclined, and I do hope all of you are, you'll find a great deal of philosophy in this, holding up a cork and a pointed thin stick about a foot long. Do not refer to your toy books and say, have you seen this before? Answer me rather if I ask you, have you understood it before? It is an experiment which appeared very wonderful to me when I was a boy. I used to take a piece of cork, and I remember I thought at first that it was very important that it should be cut out in the shape of a man, but by degrees I got rid of that idea. The problem was to balance it on the point of a stick. Now you will see I have only to place 2 sharp-pointed sticks, one on each side, and give it wings thus, and you will find this beautiful condition fulfilled. We come now to another point. All bodies, whether heavy or light, fall to the earth by this force which we call gravity. By observation, moreover, we see that bodies do not occupy the same time in falling. I think you will be able to see that this piece of paper and that ivory ball fall with different velocities to the table, dropping them now. And if again I can...
Wi-Fi for 100 miles. This is Utah. I-70. The continental divide. Here you cannot have a mobile network, you cannot make a phone call. don't have any communication other than satellite communication. The weather will be like that for 3 hours till 11 o'clock. Now it's 8 o'clock. That is from yesterday broadcast. Doesn't look bad so far. Salina Creek, no service. Of course, you won't have any service until you get to Green River, Utah. This is exit 73. From here to Green River, 90 miles. Green River is exit 160, 164. Now it is getting worse. But the snow is wet, so we should be okay until we get to high elevation 11,000, 10,000, 9,000, 8,000. That's where things are going to get worse. Because I wake up in the morning, I wake up early, I hope I can cross the continental divide between Vail and the Idaho Springs. I wish I can cross that before dark. If I can get to Denver before the sun goes down, I should be, well, we are in trouble anyway. Because from Eisenhower Tunnel to Denver is very steep, and the sun will be behind me. All I have to do now is to hope that the weather will help. They claim now, as soon as I get to Green River, Utah, before I cross the border to Colorado, that storm will be over. This is the first storm in this area for this year. And my radar is covered by the snow. The front radar is covered by the snow.
feather and an ivory ball and let them fall, you see they reach the table or earth at different times. That is to say, the ball falls faster than the feather. Now that should not be so, for all bodies do fall equally fast to the earth. There are one or two beautiful points included in that statement. First of all, it is manifest that an ounce, or a pound, or a ton, or 1,000 tons all fall equally fast, no one faster than another. Here are two balls of lead, a very light one and a very heavy one, and you perceive they both fall to earth in the same time. Now, if I were to put into a little bag a number of these balls sufficient to make up a bulk equal to the large one, they would also fall in the same time. For if an avalanche fall from the mountains, the rocks, snow, and ice, together falling toward the earth, fall with the same velocity, whatever be their size. I cannot take a better illustration of this than that of gold leaf, because it brings before us the reason of this apparent difference in the time of the fall. Here is a piece of gold leaf. Now I take a lump of gold, and this gold leaf, and let them fall through the air together. You see that the lump of gold, the sovereign or coin, will fall much faster than the gold leaf. But why? They are both gold, whether the sovereign or gold leaf. Why should they not fall to earth with the same quickness? Well, they would do so, but that the air around our globe interferes very much where we have the piece of gold so extended and enlarged as to offer such obstruction on falling through it. I will, however, show you that gold leaf does fall as fast when the resistance of the air is excluded. For I take a piece of gold leaf and hang it in the center of a bottle so that the gold and the bottle and air within shall all have an equal chance of falling, then the gold leaf will fall just as fast as anything else. And if I suspend the bottle containing the gold leaf to a string and set it oscillating like a pendulum, I may make it vibrate as hard as I please, and the gold leaf will not be disturbed, but will swing as steadily as a piece of iron would do. And I might even swing it round my head with any degree of force, and it would remain undisturbed. Or I can try another kind of experiment. If I raise the gold leaf in this way, pulling the bottle up to the ceiling of the amphitheater by means of a cord and pulley, and then suddenly letting it fall to within a few inches of the lecture table, and allow it then to fall from the ceiling downwards. I will put something beneath to catch it, supposing I should be maladroit. You will perceive that the gold leaf is not in the least disturbed, the resistance of the air having been avoided. The glass bottle and the gold leaf all fall exactly in the same time. Well, here is another illustration. I have hung a piece of gold leaf in the upper part of this long glass vessel, and I have the means, by a little arrangement at the top, of letting the gold leaf loose. Before we let it loose, we will remove the air by means of an air pump. And while that is being done, let me show you another experiment of the same kind. Take a penny piece or a half crown and a round piece of paper a trifle smaller in diameter than the coin, and try them side by side to see whether they fall at the same time, dropping them. You see, they do not. The penny piece goes down first. But now, place this paper flat on the top of the coin, so that it shall not meet with any resistance from the air, and upon then dropping them, you see they do both fall in the same time, exhibiting the effect. I dare say if I were to put this piece of gold leaf instead of the paper on the coin, it would do as well. It is very difficult to lay the gold leaf so flat that the air shall not get under it and lift it up and falling, and I am rather doubtful as to the success of this, because the gold leaf is puckery. But we'll risk the experiment. There they go together, letting them fall, and you see at once that they both reach the table at the same moment. We have now pumped the air out of the vessel, and you will perceive that the gold leaf will fall as quickly in this vacuum as the coin does in the air. I am now going to let it loose, and you must watch to see how rapidly it falls. There, letting the gold loose. There it is, falling as gold should fall. I am sorry to see how time for parting is drawing so near. As we proceed, I intend to write upon the board behind me certain words so as to recall to your minds what we have already examined, and I put the word forces as a heading, and I will then add beneath the names of the special forces according to the order in which we consider them. And although I fear that I have not sufficiently pointed out to you the more important circumstances connected with this force of gravitation, especially the law which governs its attraction, for which I think I must take up a little time in our next meeting, still I will put that word on the board and hope you will now remember that we have in some degree considered the force of gravitation, that force which causes all bodies to attract each other when they are at sensible distances apart, and tends to draw them together. End of section 2.
Section 3 of On Various Forces of Nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Sanjay Puri. On the Various Forces of Nature by Michael Faraday. Lecture 2, Part 1. Gravitation Cohesion. Do me the favor to pay me as much attention as you did at our last meeting. I shall not repent of that which I have proposed to undertake. It will be impossible for us to consider the laws of nature and what they effect, unless we now and then give our sole attention so as to obtain a clear idea of the subject. Give me now that attention, and then, I trust, we shall not part without your knowing something about those laws and the manner in which they act. You recollect, upon the last occasion, I explained that all bodies attracted each other, and that this power we call gravitation. I told you that when we brought these two bodies, two equal-sized ivory balls suspended by threads, near together, they attracted each other, and that we might suppose that the whole power of this attraction was exerted between their respective centers of gravity. And furthermore, you learned from me that if, instead of a smaller ball, I took a larger one, like that, changing one of the balls for a much larger one, there was much more of this attraction exerted. Or, if I made this ball larger and larger until, if it were possible, it became as large as the Earth itself, or I might take the Earth itself as the large ball, and then the attraction becomes so powerful as to cause them to rush together in this manner, dropping the ivory ball. You sit there, upright, and I stand upright here, because we keep our centers of gravity properly balanced with respect to the Earth. And I need not tell you that on the other side of this world, the people are standing and moving about with their feet towards our feet, in a reversed position as compared with us. And all by means of this power of gravitation to the center of the Earth. I must not, however, leave the subject of gravitation without telling you something about its laws and regularity. And first, as regards its power, with respect to the distance that bodies are apart. If I take one of these balls and place it within an inch of the other, they attract each other with a certain power. If I hold it at a greater distance off, they attract with less power. And if I hold it at a greater distance still, their attraction is still less. Now this fact is of the greatest consequence, for knowing this law, philosophers have discovered most wonderful things. You know that there is a planet Uranus revolving round the Sun with us, but 1,800 millions of miles off. And because there is another planet as far off as 3,000 millions of miles, this law of attraction or gravitation still holds good, and philosophers actually discovered this latter planet, Neptune, by reason of the effects of its attraction at this overwhelming distance. Now I want you clearly to understand what this law is. They say, and they are right, that two bodies attract each other inversely as the square of the distance. A sad jumble of words until you understand them, but I think we should soon comprehend what this law is and what is the meaning of this inverse square of the distance. I have here, figure 11, a lamp A, shining most intensely upon this disk, BCD. And this light acts as a sun by which I can get a shadow from this little screen, F, merely a square piece of card which, as you know, when I place it close to the large screen, just shadows as much of it as is exactly equal to its own size. But now let me take this card E, which is equal to the other one in size, and place it midway between the lamp and the screen. Now look at the size of the shadow ET. It is 4 times the original size. Here then comes the inverse square of the distance. This distance, AE, is 1, and that distance, AB, is 2. But that size, E, 1, this size, BD, of shadow is 4 instead of 2, which is the square of the distance. And if I put the screen at 1/3 of the distance from the map, the shadow of the large screen will be 9 times the size. Again, if I hold the screen here at BF, a certain amount of light falls on it, and if I hold it nearer the lamp at E, more light shines upon it. And you see at once how much exactly the quantity which I have shut off from the part of the screen BD, now in shadow. Moreover, you see that if I put a single screen here at G, by the side of the shadow, it can only receive 1/4 the portion of light which is obstructed. That then is what is meant by the inverse of the square of the distance. This screen E is the brightest because it is the nearest, and there is the whole secret of this curious expression, inversely as the square of the distance. Now, if you cannot perfectly recollect this when you go home, get a candle and throw a shadow of something, your profile if you want, on the wall, and then recede or advance, and you will find that your shadow is exactly in proportion to the square of the distance you are off the wall. And then, if you consider how much light shines on you at one distance, and how much at another, you get the inverse accordingly. So it is as regards the attraction of these two laws. They attract according to the square of the distance, inversely. I want you to try and remember these words, and then you will be able to go into all the calculations of astronomers as to the planets and other bodies, and tell why they move so fast, and why they go around the sun without falling into it, and be prepared to enter upon many other interesting inquiries of the like nature. Let us now leave the subject which I have written upon the board under the word force gravitation and go a step further. All bodies attract each other at sensible distances. I showed you the electric attraction on the last occasion, though I did not call it so, that attracts at a distance, and in order to make our progress a little more gradual, suppose I take a few iron particles, dropping some small fragments of iron in the table. There, I have already told you that in all cases where bodies fall, it is the particles that are attracted. You may consider these then as separate particles magnified, so as to be evident to your sight. they are loose from each other, they all gravitate, they all fall to the earth, for the force of gravitation never fails. Now, I have here a center of power, which I will not name at present, and when these particles are placed upon, see what an attraction they have for each other. Here I have an arch of iron filings, figure 12, regularly built up like an iron bridge, because I have put them within a sphere of action which will cause them to attract each other. See, I could let a mouse run through, and yet, if I try to do the same thing with them here on the table, they do not attract each other at all. It is that, the magnet, which makes them hold together. Now, just as these iron particles hold together in the form of an elliptical bridge, so do the different particles of iron, which constitute this nail, hold together and make it one. And here is a bar of iron. Why? It is only because the different parts of this iron are so wrought as to keep close together by the attraction between the particles that it is held together in one mass. It is kept together, in fact, merely by the attraction of one particle to another, and that is the point I want now to illustrate. If I take a piece of flint and strike it with a hammer and break it thus, breaking off a piece of the flint, I have done nothing more than separate the particles which compose these two pieces so far apart that their attraction is too weak to cause them to hold together. And it is only for that reason that there are now two pieces in the place of one. I will show you an experiment to prove that this attraction does still exist in those particles. For here is a piece of glass. For what was true of the flint and the bar of iron is true of the piece of glass, and is true of every other solid. They are all held together in the lump by the attraction between their parts. And I can show you the attraction between its separate particles. For if I take these portions of glass, which I have reduced to very fine powder, you see that I can actually build them up into a solid wall by pressure between two flat surfaces. The power which I thus have of building up this wall is due to the attraction of the particles, forming as it were the cement which holds them together. And so in this case, when I have taken no very great pains to bring the particles together, you see perhaps a couple of ounces of finely pounded glass standing as an upright wall. Is not this attraction most wonderful? That bar of iron, 1 inch square, has such power of attraction in its particles, giving to it such strength that it will hold up 20 tons weight before the little set of particles in the small space equal to one division across, which can be pulled apart and separate. In this manner, suspension bridges and chains are held together by the attraction of their particles, and I am going to make an experiment which will show how strong is this attraction of the particles. The lecturer here placed his foot on a loop of wire fastened to a support above, and swung with his whole weight resting upon it for some moments. You see, while hanging here, all my weight is supported by these little particles of wire, just as in pantomimes they sometimes suspend gentlemen and damsels. How can we make this attraction of the particles a little more simple? There are many things which, if brought together properly, will show this attraction. Here is a boy's experiment, and I like a boy's experiment. Get a tobacco pipe, fill it with lead, melt it, and then pour it out upon the stove, and thus get a clean piece of lead. This is a better plan than scraping it. Scraping alters the condition of the surface of the lead. I have here some pieces of lead, which I melted this morning, for the sake of making them clean. Now these pieces of lead hang together by the attraction of their particles, and if I press these two separate pieces close together, so as to bring their particles within the sphere of attraction, you will see how soon they become one. I have merely to give them a squeeze and draw draw the upper peaks slightly round at the same time, and here they are as one. And all the bending and twisting I can give them will not separate them again. I have joined the lead together not with solder, but simply by means of the attraction of the particles. This, however, is not the best way of bringing those particles together. We have many better plans than that, and I will show you one that will do very well for juvenile experiments. There is some alum crystallized very beautifully by nature, for all things are far more beautiful in their natural than their artificial form. And here I have some of the same alum broken into fine powder. In it, I have destroyed that force of which I have placed the name on this board, cohesion, or the attraction exerted between the particles of bodies to hold them together. Now I am going to show you that if we take this powdered alum and some hot water and mix them together, I should dissolve the alum, all the particles will be separated by the water far more completely than they are here in the powder. But then, being in the water, they will have the opportunity as it cools, for that is the condition which favors their coalescence, of uniting together again and forming one mass. Now, having brought the alum into solution, I will pour it into this glass basin, and you will tomorrow find that those particles of alum which I have put into the water and so separated that they are no longer solid, will, as the water cools, come together and cohere, and by tomorrow morning we shall have a great deal of the alum crystallized out, that is to say, come back to the solid form. The lecturer here poured a little of the hot solution of alum into the glass dish, and when the latter had thus been made warm, the remainder of the solution was added. I am now doing that which I advise you to do if you use a glass vessel, namely, warming it slowly and gradually, and in repeating this experiment, do as I do, pour the liquid out gently, leaving all the dirt behind in the basin. And remember that the more carefully and quietly you make this experiment at home, the better the crystals. Tomorrow you will see the particles of alum form together, and if I put 2 pieces of coke in some part of the solution, the coke ought first to be washed very clean and dry, you will find tomorrow that we shall have a beautiful crystallization over the coke, making it exactly resemble a natural mirror. Now, how curiously our ideas expand by watching these conditions of the attraction of cohesion. How many new phenomena it gives us beyond those of the attraction of gravitation. See how it gives us great strength. The things we deal with in building up the structures of the earth are of strength. Use iron, stone, and other things of great strength. And only think that all those structures you have about, if you please, which is of such size and power as to be almost more than man can manage, are the result of this power of cohesion and attraction. I have here a body in which I believe you will see a change taking place in this condition of cohesion at the moment it is made. It is at first yellow. It then becomes a fine crimson red. Just watch when I pour these 2 liquids together, both colorless as water. The lecturer here mixed together solutions of perchloride of mercury and iodide of potassium, when a yellow precipitate of iodide of mercury fell down, which almost immediately became crimson red. Now there is a substance which is very beautiful, but see how it is changing color. It was reddish yellow at first, but it has now become red. I have previously prepared a little of this red substance, which you see formed in the liquid, and have put some of it upon paper, exhibiting several sheets of paper coated with scarlet biiodide of mercury. There it is, the same substance spread upon paper, and there too is the same substance, and here is some more of it, exhibiting a piece of paper as large as the other sheets, but having only very little red color on it, the greater part being yellow. A little more of it, you would say. Do not be mistaken. There is as much upon the surface of one of these pieces of paper as upon the other. What you see yellow is the same thing as the red body, only the attraction of cohesion is in a certain degree changed. For I will take this red body and apply heat to it. You may perhaps see a little smoke arise, but that is of no consequence. And if you look at it, it will first of all darken, but see how it is becoming yellow. I have now made it all yellow. What is more, it will remain so. But if I take any hard substance and rub the yellow part with it, it will immediately go back again to the red condition. Exhibiting the experiment. There it is. You see, the red is not put back, but brought back by the change of the substance. Now, warming it over the spirit lamp, here it is becoming yellow again. And that is all because its attraction of cohesion has changed. And what will you say to me when I tell you that this piece of common charcoal is just the same thing, only differently coalesced as the diamonds which you wear? I have put a specimen outside of a piece of straw which was charred in a particular way. It is just like black lead. Now, this charred straw, this charcoal, and these diamonds are all of them the same substance, changed but in their properties as respects the force of rotation. End of section 3. Section 4 of On the Various Forces of Nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Sanjay Praveen. On the Various Forces of Nature by Michael Faraday. Lecture 2, Part 2, Gravitation Cohesion. Here is a piece of glass, producing a piece of plate glass about 2 inches square. I shall want this afterwards to look to and examine its internal condition. And here is some of the same sort of glass, differing only in its power of cohesion, because while yet melted, it has been dropped into cold water, exhibiting a Prince Rupert's drop, figure 13. And if I take one of these little tear-like pieces and break off ever so little from the point, the whole will at once burst and fall to pieces. I will now break off a piece of this. The lecturer nipped off a small piece from the end of one of the Rupert's drops, whereupon the whole immediately fell to pieces. There, see, the solid glass has suddenly become powder, and more than that, it has knocked a hole in the glass vessel in which it was held. I can shew the effect better in this bottle of water, and it is very likely the whole bottle will go. A 6-ounce vial was filled with water, and a Rupert's drop placed in it, with the point of the tail just projecting out. Upon breaking the tip off, the drop burst, and the shock being transmitted through the water to the sides of the bottle shattered the latter to pieces. Here is another form of the same kind of experiment. I have here some more glass, which has not been annealed, showing some thick glass vessels, figure 14. And if I take one of these glass vessels and drop a piece of pounded glass into it, or I will take some of these small pieces of rock crystal, they have the advantage of being harder than glass, and so make the least scratch upon the inside, the whole bottle will break to pieces. It cannot hold together. The lecturer here dropped a small fragment of rock crystal into one of these glass vessels, when the bottom immediately came out and fell upon the plate. There, it goes through just as it would through the sea. Now, I have shewn you these things for the purpose of bringing your minds to see that bodies are not merely held together by this power of cohesion, but that they are held together in very curious ways. And suppose I take some things that are held together by this force and examine them more minutely. I will first take a bit of glass, and if I give it a blow with a hammer, I should just break it to pieces. You saw how it was in the case of the flint, when I broke the piece off. A piece of a similar kind would come off, just as you would expect. And if I were to break it up still more, it would be, as you have seen, simply a collection of small particles of no definite shape or form. But supposing I take some other thing, this stone for instance, figure 15, taking a piece of mica, and if I hammer this stone, I may batter it a great deal before I can break it up. I may even bend it without breaking it. That is to say, I may bend it in one particular direction without breaking it much, although I feel in my hands that I am doing it some injury. But now, if I take it by the edges, I find that it breaks up into leaf after leaf in a most extraordinary manner. Why should it break up like that? Not because all stones do, or all crystals, for there is some salt, figure 16. You know what common salt is. Here is a piece of this salt, which by natural circumstances has had its particles so brought together that they have been allowed free opportunity of combining or coalescing. And you shall see what happens if I take this piece of salt and break it. It does not break as flint did, or as the mica did, but with a clean, sharp angle and exact surfaces, beautiful and glittering as diamonds, breaking it by gentle blows with a hammer. There is a square prism which I may break up into a square cube. You see, these fragments are all square. One side may be longer than the other, they will only split up so as to form square or oblong pieces with cubical sides. Now, I go a little further and I find another stone, figure 17, iceland or calc-spar, which I may break in a similar way, but not with the same result. Here is a piece which I have broken off, and you see there are plane surfaces perfectly regular with respect to each other. But it is not cubical. It is what we call a rhomboid. It still breaks in three directions, most beautifully and regularly, with polished surfaces, but with sloping sides, not like the sword. Why not? It is very manifest that this is owing to the attraction of the particles, one for the other, being less in the direction in which they give way than in other directions. I have on the table before me a number of little bits of calcareous spar, and I recommend each of you to take a piece home. And then you can take a knife and try to divide it in the direction of any of the surfaces already existing. You will be able to do it at once, but if you try to cut it across the crystals, you cannot. By hammering you may bruise and break it up, but you can only divide it into these beautiful little rhomboids. Now I want you to understand a little more how this is, and for this purpose I'm going to use the electric light again. You see, we cannot look into the middle of a body like this piece of glass. We perceive the outside form and the inside form, and we look through it, but we cannot well find out how these forms become so. And I want you, therefore, to take a lesson in the way in which we use a ray of light for the purpose of seeing what is in the interior of bodies. Light is a thing which is, so to say, attracted by every substance that gravitates, and we do not know anything that does not. All matter affects light more or less by what we may consider as a kind of attraction. And I have arranged, figure 18, a very simple experiment on the floor of the room for the purpose of illustrating this. I have put into that basin a few things which those who are in the body of the theatre will not be able to see, and I'm going to make use of this power which matter possesses of attracting a ray of light. If Mr. Anderson pours some water gently and steadily into the basin, water will attract the rays of light downwards. and the piece of silver and the sealing wax will appear to rise up into the sight of those who were before not high enough to seal. Mr. Anderson here poured water into the basin, and upon the lecturer asking whether anybody could see the silver and sealing wax, he was answered by a general affirmative. Now, I suppose that everybody can see that they are not at all disturbed, whilst from the way they appear to have risen up, you would imagine the bottom of the basin and the articles in it were 2 inches thick, although they are only one of our small silver dishes and a piece of sealing wax which I have put there. The light which now goes to you from that piece of silver was obstructed by the edge of the basin, when there was no water there, and you were unable to see anything within. But when we poured in water, the rays were attracted down by it, over the edge of the basin, and you were thus enabled to see the articles at the bottom. I have shewn you this experiment first, so that you might understand how glass attracts light, and might then see how other substances, like rock salt and calcareous spar, mica, and other stones will affect the light. And if Dr. Tyndall will be good enough to let us use his light again, we will first of all show you how it may be bent by a piece of glass. Figure 19. The electric lamp was again lit, and the beam of parallel rays of light which it emitted was bent about and decomposed by means of the prism. Now, here you see, if I send the light through this piece of plain glass, A, it goes straight through, without being bent, unless the glass be held obliquely, and then the phenomenon becomes more complicated. But if I take this piece of glass, B, a prism, you see it will shew a very different effect. It no longer goes to that wall, but it is bent to the screen, C. And how much more beautiful it is now, throwing the prismatic spectrum on the screen. This ray of light is bent out of its course by the attraction of the glass upon it. And you see I can turn and twist the rays to and fro in different parts of the room, just as I please. Now it goes there, now here. The lecturer projected the prismatic spectrum about the theatre. Here I have the rays once more bent onto the screen, and you see how wonderfully and beautifully that piece of glass not only bends the light by virtue of its attraction, but actually splits it up into different colors. Now, I want you to understand that this piece of glass, the prism, being perfectly uniform in its internal structure, tells us about the action of these other bodies which are not uniform, which do not merely cohere, but also have within them, in different parts, different degrees of cohesion, and thus attract and bend the light with varying powers. We will now let the light pass through one or two of these things, which I just now showed you, broke so curiously. And first of all, I will take a piece of mica. Here, you see, is our ray of light. And first to make it what we call polarized. But about that, you need not trouble yourself. It is only to make our illustration more clear. Here then, we have our polarized ray of light, as to make the screen upon which it is shining either light or dark, although I have nothing in the course of this ray of light but what is perfectly transparent. Turning the analyzer around, I will now make it so that it is quite dark, and we will, in the first instance, put a piece of common glass into the polarized ray, so as to show you that it does not enable the light to get through. You see the screen remains dark. The glass then internally has no effect upon the light. The glass was removed and a piece of mica introduced. Now, there is the mica which we split up so curiously into leaf after leaf, and see how that enables the light to pass through to the screen, and how, as Dr. Tyndall turns it round in his hand, you have those different colors, pink and purple and green, coming and going most beautifully, not that the mica is more transparent than the glass, but because of the different manner in which its particles are arranged by the force of cohesion. Now we will see how calcareous spar acts upon this light. That stone which split up into rhombs, and of which you are each of you going to take a little piece home. The mica was removed and a piece of calc spar introduced at A. See how that turns the light round and round and produces these rings and that black cross, figure 20. Look at those colors. Are they not most beautiful for you and me? For I enjoy these things as much as you do. In what a wonderful manner they open out to us the internal arrangement of the particles of this calcareous spar by the force of cohesion. And now I will shew you another experiment. Here is that piece of glass which before had no action upon the light. You shall see what it will do when we apply pressure to it. Here then we have our ray of polarized light, and I will first of all shew you that the glass has no effect on it in its ordinary state. When I place it in the course of the light, the screen still remains dark. Now Dr. Tyndall will press that bit of glass between three little points, one point against two, so as to bring a strain upon the parts, and you will see what a curious effect that has. Upon the screen, two white dots gradually appeared. Ah, these points shew the position of the strain. In these parts, the force of cohesion is being exerted in a different degree to what it is in the other parts, and hence it allows the light to pass through. How beautiful that is! How it makes the light come. bottom and sides all together formed like a sieve, and yet in cold water, owing to this cohesion. You have now seen that the solid water can become fluid by the addition of heat, owing to this lessening the attractive force between its particles. And yet you see that there is a good deal of attractive force remaining behind. I want now to take you another step beyond. We saw that if we continued applying heat to the water, as indeed happened with our piece of ice here, that we did at last break up that attraction which holds the liquid together. And I am about to take some ether. Any other liquid would do, but ether makes a better experiment for my purpose, in order to illustrate what will happen when this cohesion is broken up. Now, this liquid ether, if exposed to a very low temperature, will become a solid. But if we apply heat to it, it becomes a vapor. And I want to show you the enormous bulk of the substance in this new form. When we make ice into water, we lessen its bulk. But when we convert water into steam, we increase it to an enormous extent. You see, it is very clear that as I apply heat to the liquid, I diminish its attraction of cohesion. It is now boiling, and I will set fire to the vapor so that you may be enabled to judge of the space occupied by the ether in this form by the size of its flame. And you now see what an enormously bulky flame I get from the small volume of ether below. The heat from the spirit lamp is now being consumed, not in making the ether any warmer, but in converting it into vapor. And if I desired to catch this vapor and condense it, as I could without much difficulty, I should have to do the same as if I wished to convert steam into water and water into ice. In either case, it would be necessary to increase the attraction of the particles by cold or otherwise. So largely is the bulk occupied by the particles increased by giving them this diminished attraction, that if I were to take a portion of water, a cubic inch in bulk, A, figure 23, I should produce a volume of steam of that size B, 1700 cubic inches, nearly a cubic foot. So greatly is the attraction of cohesion diminished by heat, and yet it still remains water. You can easily imagine the consequences which are due to this change in volume by heat. The mighty powers of steam and the tremendous explosions which are sometimes produced by this force of water. I want you now to see another experiment, which will perhaps give you a better illustration of the bulk occupied by a body when in the state of vapor. Here is the substance which we call iodine, and I am about to submit this solid body to the same kind of condition as regards heat that I did for water and the ether. Putting a few grains of iodine into a hot glass globe, which immediately became filled with the violet vapor. And you see the same kind of change produced. Moreover, it gives us the opportunity of observing how beautiful is the violet-colored vapor from this black substance, or rather, the mixture of the vapor with air. For I would not wish you to understand that this globe is entirely filled with the vapor of iodine. If I had taken mercury and converted it into vapor, as I could easily do, I should have a perfectly colorless vapor. For you must understand this about vapors, that bodies, what we call the vaporous or the gaseous state, are always perfectly transparent, never cloudy or smoky. They are, however, often colored, and we can frequently have colored vapors or gases produced by colorless particles themselves, mixing together, as in this case. The lecturer here inverted a glass cylinder full of binoxide of nitrogen over a cylinder of oxygen when the dark red vapor of hyponitrous acid was produced. Here also you see a very excellent illustration of the effect of a power of nature which come to, but which stands next on our list: chemical affinity. End of section 5. Section 6 of On the Various Forces of Nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Sanjay Purita. On the Various Forces of Nature by Michael Fallon. Lecture 3, Part 2. Fusion. Chemical affinity. And thus you see we can have a violet vapor or an orange vapor and different other kinds of vapor, but they are always perfectly transparent, or else they would cease to be vapors. I'm now going to move you a step beyond this consideration of the attraction of the particles from each other. You see, we have come to understand that if we take water as an illustration, whether it be ice or water or steam, it is always to be considered by us as water. Well, now prepare your minds to go a little deeper into the subject. We have means of searching into the constitution of water beyond any that are afforded us by the action of heat, and among these, one of the most important is that force which we call, take, electricity, which we used at our last meeting for the purpose of obtaining light, and which we carried about the room by means of these wires. This force is produced by the battery behind me, to which, however, I will not now refer more particularly. Before we have done, we shall know more about this battery, but it must grow up in our knowledge as we proceed. Now here, figure 24, is a portion of water in this little vessel C. And besides the water, there are two plates of the metal battlement, which are connected to the wires A and B, coming outside. And I want to examine that water and the state and the condition in which its particles are arranged. If I were to apply heat to it, you know what we should get. It would assume the state of vapor, but it would nevertheless remain water, and it would turn to the liquid state as soon as the heat is removed. Now, by means of these wires, which are connected with the battery behind me and come under the floor and up through the table, we shall have a certain amount of this new power at our disposal. Here you see it is causing the ends of the wires to touch. That is the electric light we used yesterday, and by means of these wires, we can cause water to submit itself to this power. For the moment, I put them into metallic connection at A and B. You see the water boiling in that little vessel, C, and you hear the bubbling of the gas that is going through to D. See how I am converting the water into vapor. And if I take a little vessel E and fill it with water and put it in the trough over the end of the tube D, there goes the vapor ascending into the vessel. And yet, that is not steam. For you know that if steam is brought near cold water, it would at once condense and return back again to water. This then cannot be steam, for it is bubbling through the cold water in this trough. But it is a vaporous substance, and we must therefore examine it carefully to see in what way the water has been changed. And now, in order to give you proof that it is not steam, I'm going to show you that it is combustible. For if I take this small vessel to a light, the vapor inside explodes in a manner that steam could never do. I will now fill this large bell jar, F, with water, and I propose letting the gas ascend into it. And I will then show you that we can reproduce the water back again from the vapor or air that is there. Here is a strong glass vessel, G, and into it we will let the gas from F pass. We will their firing by the electric spark. Very well as a comparison effect produced by air and oxygen. If I take this ring flame, I can shake by means of a sieve the fine particles of iron filings through it, and you will see the way in which they burn. The lecturer here shook through the flame some iron filings, which took fire and fell through with beautiful scintillations. But if I now hold the flame over a jar of oxygen, the experiment was repeated over a jar of oxygen when the combustion of the filings, as they fell into the oxygen, became almost insupportably brilliant. You will see how wonderfully different the effect is in the jar, because there we have oxygen instead of common air. End of section 6.
Section 7 on the various forces of nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Michelle Fry, Dr. Louisiana, in June 2021. On the various forces of nature by Michael Faraday. Section 7. Lecture 4, Chemical Affinity, Heat. We shall have to pay a little more attention to the forces existing in water before we can have a clear idea on the subject. Besides the attraction which there is between its particles to make it hold together as a liquid or a solid, there is also another force, different from the former, one which yesterday, by means of the voltaic boundary, we overcame, drawing from the water two different substances, which, when heated by means of the electric spark, attracted each other and rushed into combination to reproduce water. Now I propose today to continue this subject and trace the various phenomena of chemical affinity. And for this purpose, as we yesterday considered the character of oxygen, of which I have here 2 jars, oxygen being those particles derived from the water which enable other bodies to burn, we will now consider the other constituent of water. And without embarrassing you too much with the way in which these things are made, I will proceed now to show you our common way of making hydrogen. I called it hydrogen yesterday. It is so called because it helps to generate water. I put into this retort some zinc, water, and oil of vitriol, and immediately an action takes place which produces an abundant evolution of gas, now coming over into this jar and bubbling up in appearance exactly like the oxygen we obtained yesterday. The processes, you see, are very different, though the result is the same, insofar as it gives us certain gaseous particles. Here, then, is the hydrogen. I showed you yesterday certain qualities of this gas. Now let me exhibit you some other properties. Unlike oxygen, which is a supporter of combustion and will not burn, hydrogen itself is combustible. There is a jar full of it, and if I carry it along in this manner and put a light to it, I think you will see it take fire, not with a bright light. You will at all events hear it if you do not see it. Now that is a body entirely different from oxygen. It is extremely light, for although yesterday you saw twice as much of this hydrogen produced on the one side as on the other by the voltaic battery, it was only 1/8 the weight of oxygen. I carry this jar upside down. Why? Because I know that it is a very light body, and that it will continue in this jar upside down quite as effectually as the water will in that jar which is not upside down. And just as I can pour water from one vessel into another in the right position to receive it, so can I pour this gas from one jar into another when they are upside down. See what I am about to do. There is no hydrogen in this jar at present, but I will gently turn this jar of hydrogen up under this other jar, figure 28, and then we will examine the two. We shall see, on applying a light, that the hydrogen has left the jar in which it was at first, and is poured upwards into the other. And there we shall find it. You now understand that we can have particles of very different kinds, and that they can have different bulks and weights. And there are 2 or 3 very interesting experiments which serve to illustrate this. For instance, if I blow soap bubbles with the breath from my mouth, you will see them fall, because I fill them with common air, and the water which forms the bubble carries it down. But now, if I inhale hydrogen gas into my lungs, it does no harm to the lungs, although it does no good to them. See what happens. Parentheses, the lecturer inhaled some hydrogen, and after 1 or 2 ineffectual attempts, succeeded in blowing a very splendid bubble, which rose majestically and slowly to the ceiling of the theater, where it burst. Close parentheses. That shows you very well how light a substance this is. For notwithstanding all the heavy, bad air from my lungs and the weight of the bubble, you saw how it was carried up. I want you now to consider this phenomenon of weight as indicating how exceedingly different particles are one from the other, and I will take as illustrations these very common things: air, water, the heaviest body, platinum, and this gas, and observe how they differ in this respect. For if I take a piece of platinum of that size, figure 29, it is equal
When we make ice into water, we lessen its bulk. But when we convert water into steam, we increase it to an enormous extent. You see, it is very clear that as I apply heat to the liquid, I diminish its attraction of cohesion. It is now boiling, and I will set fire to the vapor so that you may be enabled to judge of the space occupied by the ether in this form by the size of its flame. And you now see what an enormously bulky flame I get from the small volume of ether below. The heat from the spirit lamp is now being consumed, not in making the ether any warmer, but in converting it into vapor. And if I desired to catch this vapor and condense it, as I could without much difficulty, I should have to do the same as if I wished to convert steam into water and water into ice. In either case, it would be necessary to increase the attraction of the particles by cold or otherwise. So largely is the bulk occupied by the particles increased by giving them this diminished attraction, that if I were to take a portion of water, a cubic inch in bulk, A, figure 23, I should produce a volume of steam of that size B, 1700 cubic inches, nearly a cubic foot. So greatly is the attraction of cohesion diminished by heat, and yet it still remains water. You can easily imagine the consequences which are due to this change in volume by heat. The mighty powers of steam and the tremendous explosions which are sometimes produced by this force of water. I want you now to see another experiment, which will perhaps give you a better illustration of the bulk occupied by a body when in the state of vapor. Here is the substance which we call iodine, and I am about to submit this solid body to the same kind of condition as regards heat that I did the water and the ether. Putting a few grains of iodine into a hot glass globe, which immediately became filled with the violet vapor. And you see the same kind of change produced. Moreover, it gives us the opportunity of observing how beautiful is the violet-colored vapor from this black substance, or rather, the mixture of the vapor with air. For I would not wish you to understand that this globe is entirely filled with the vapor of iodine. If I had taken mercury and converted it into vapor, as I could easily do, I should have a perfectly colorless vapor. For you must understand this about vapors, that bodies, what we call the vaporous or the gaseous state, are always perfectly transparent, never cloudy or smoky. They are, however, often colored, and we can frequently have colored vapors or gases produced by colorless particles themselves mixing together, as in this case. The lecturer here inverted a glass cylinder full of binoxide of nitrogen over a cylinder of oxygen when the dark red vapor of hyponitrous acid was produced. Here also you see a very excellent illustration of the effect of a power of nature which we have not as yet come to, but which stands next on our list: chemical affinity. End of section 5. Section 6 of On the Various Forces of Nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Sanjay Parikh. On the Various Forces of Nature by Michael Faraday. Lecture 3, Part 2. Cohesion. Chemical affinity. And thus you see we can have a violet vapor or an orange vapor and different other kinds of vapor, but they are always perfectly transparent. It cease to be vapors. I'm now going to lead you a step beyond this consideration of the attraction of the particles from each other. You see, we have come to understand that if we take water as an illustration, whether it be ice or water or steam, it is always to be considered by us as water. Well, now prepare your minds to go a little deeper into the subject. We have means of searching into the constitution of water beyond any that are afforded us by the action of heat, and among these, one of the most important is that force which we call voltaic electricity, which we used at our last meeting for the purpose of obtaining light, and which we carried about the room by means of these wires. This force is produced by the battery behind me, to which, however, I will not now refer more particularly. Before we have done, we shall know more about this battery, but it must grow up in our knowledge as we proceed. Now here, figure 24, is a portion of water in this little vessel C, and besides the water, there are two plates of the metal platinum, which are connected with the wires A and B coming outside. And I want to examine that water and the state and the condition in which its particles are arranged. If I were to apply heat to it, you know what we should get. It would assume the state of vapor, but it would nevertheless remain water, and would return to the liquid state as soon as the heat was removed. Now, by means of these wires, which are connected with the battery behind me, and come under the floor and up through the table, we shall have a certain amount of this new power at our disposal. Here you see, it is causing the ends of the wires to touch. That is, the electric light we used yesterday. And by means of these wires, we can cause water to submit itself to this power. For the moment, I put them into metallic connection at A and B. You see the water boiling in that little vessel, C, and you hear the bubbling of the gas that is going through the tube, D. See how I am converting the water into vapor. And if I take a little vessel, E, and fill it with water, and put it in the trough over the end of the tube, D, there goes the vapor ascending into the vessel. And yet, that is not steam. For you know that if steam is brought near cold water, it would at once condense and return back again to water. This then cannot be steam, for it is bubbling through the cold water in this trough. But it is a vaporous substance, and we must therefore examine it carefully to see in what way the water has been changed. And now, in order to give you proof that it is not steam, I'm going to show you that it is combustible. For if I take this small vessel to a light, the vapor inside explodes in a manner that steam could never do. I will now fill this large bell jar, F, with water, and I propose letting the gas ascend into it. And I will then show you that we can reproduce the water back again from the vapor or air that is there. Here is a strong glass vessel, G, and into it we will let the gas from F pass. We will there fire it by the electric spark, and then, after the explosion, we will find that we have got the water back again. It will not be much, however, for you will recollect that I showed you how small a portion of water produced a very large volume of vapor. Mr. Anderson will now pump all the air out of this vessel G, and when I have screwed it onto the top of our jar of gas F, you will see upon opening the stopcocks H', H, H, the water will jump up, showing that some of the gas has passed into the glass vessel. I will now shut these stopcocks, and we shall be able to send the electric spark through the gas by means of the wires IK in the upper part of the vessel, and you will see it burn with a most intense flash. Mr. Anderson here brought a laden jar, which he discharged through the confined gas by means of the wires IK. You saw the flash? And now that you may see that there is no longer any gas remaining, if I place it over the jar and open the stopcocks again, up will go the gas, and we can have a second combustion. And so I might go on, again and again, and I should continue to accumulate more and more of the water to which the gas has returned. Now, is this not curious? In this vessel, see, we can go on making from water a large bulk of permanent gas, as we call it, and then we can reconvert it into water in this way. Mr. Anderson brought in another leaded jar, which, however, from some cause, would not ignite the gas. It was therefore recharged when the explosion took place in the desired manner. How beautifully we get our results when we are right in our proceeding. It is not that nature is wrong when we make a mistake. Now, I will lay this vessel, G, down by my right hand, and you can examine it by and by. There is not very much water flowing down, but there is quite sufficient for you to see. Another wonderful thing about this mode of changing the condition of the water is this, that we are able to get the separate parts of which it is composed, at a distance the one from the other, and to examine them and see what they are like, and how many of them there are. And for this purpose, I have here some more water in a slightly different apparatus to the former one, figure 25. And if I place this in connection with the wires of the battery at A, B, I shall get a similar decomposition of the water at the two platinum plates. Now, I will put this little tube, O, over there, and that will collect the gas together that comes from this side, A, and this tube H will collect the gas that comes from the other side, B. And I think we shall soon be able to see a difference. In this apparatus, the wires are a good way apart from each other, and it now seems that each of them is capable of drawing off particles from the water and sending them off. And you see that one set of particles, H, is coming off twice as fast as those collected in the other tube, O. Something is coming out of the water there at H, which burns, setting fire to the gas. But what comes out of the water here at O, although it will not burn, will support combustion very vigorously. The lecturer here placed a match with a glowing tip in the gas when it immediately rekindled. Here then, we have two things, neither of them being water alone, but which we get out of the water. Water is therefore composed of two substances, different to itself, which appear at separate places when it is made to submit to the force which I have in these wires. And if I take an inverted tube of water and collect this gas, H, you will see that it is by no means the same as the one we collected in the former apparatus, figure 24. That exploded with a loud noise when it was lighted, but this will burn quite noiselessly. It is called hydrogen, and the other we call oxygen. That gas which so beautifully brightens up all combustion, but does not burn off itself. So now we see that water consists of two kinds of particles attracting each other in a very different manner to the attraction of gravitation or cohesion. And this new attraction we call chemical affinity, or the force of chemical action between different bodies. We are now no longer concerned with the attraction of iron for iron, water for water, wood for wood, or like bodies for each other, as we were when dealing with the force of cohesion. We are dealing with another kind of attraction, the attraction between particles of a different nature, one to the other. Chemical affinity depends entirely upon the energy with which particles of different kinds attract each other. Oxygen and hydrogen are particles of different kinds, and it is their attraction to each other which makes them chemically combine and produce water. I must now show you a little more at large what chemical affinity is. I can prepare these gases from other substances, as well as from water. And we will now prepare some oxygen. Here is another substance which contains oxygen, chlorate of potash. I will put some of this into this glass retort, and Mr. Anderson will apply heat to it. We have here different jars filled with water, and when, by the application of heat, the chlorate of potash is decomposed, we will displace the water and fill the jars with gas. Now, when water is opened out in this way by means of the battery, which adds nothing to it materially, which takes nothing from it materially, I mean no matter, I am speaking of force, which adds no matter to the water, it is changed in this way. The gas which you saw burning a little while ago, called hydrogen, is evolved in large quantity, and the other gas, oxygen, is evolved in only half the quantity, so that these two areas represent water, and these are always proportions between the two gases. But oxygen is 16 times the weight of the other, 8 times as heavy as the particles of hydrogen in the water, and you therefore know that water is composed of 9 parts by weight, 1 of hydrogen and 8 of oxygen. Thus, hydrogen, 46.2 cubic inches, is equal to 1 grain. Oxygen, 23.1 cubic inches, is equal to 8 grains. Water, steam, 69.3 cubic inches, is equal to 9 grains. Now, Mr. Anderson has prepared some oxygen, and we will proceed to examine what is the character of this gas. First of all, you remember I told you that it does not burn, but that it affects the burning of other bodies. I will just set fire to the point of this little bit of wood, and then plunge it into the jar of oxygen, and you will see what this gas does in increasing the brilliancy of the combustion. It does not burn, it does not take fire as the hydrogen would, but how vividly combustion of the match goes on. Again, if I were to take this wax taper and light it and turn it upside down in the air, it would in all probability put itself out, owing to the wax running down into the wick. The lecturer here turned the lighted taper upside down when in a few seconds it went out. Now that will not happen in oxygen gas. You will see how differently it acts.
the high elevations before the sun goes down. We are doing good. It's now 12 o'clock, 12:28, and we have 200 miles to get to Denver, which is not bad at all. So I should be in Denver before 5 o'clock, before the sun goes down. Assuming that the high elevations don't have snow. There is a warning that severe weather at high elevations might not happen on the I-70. We might be able to get through without a problem because the temperature here is 44 degrees. And we are at almost 7,000 feet elevation.
The taper was again lighted, turned upside down, and then introduced into a jar of oxygen. Look at that. See how the very wax itself burns and falls down in a dazzling stream of fire. So powerfully does the oxygen support combustion. Again, here is another experiment which will serve to illustrate the force, if I may so call it, of oxygen. I have here a circular flame of spirit of wine, and with it I am about to show you the way in which iron burns, because it will serve very well as a comparison between the effect produced by air and oxygen. If I take this ring flame, I can shake by means of a sieve the fine particles of iron filings through it, and you will see the way in which they burn. The lecturer here shook through the flame some iron filings, which took fire and fell through with beautiful scintillations. But if I now hold the flame over a jar of oxygen, experiment was repeated over a jar of oxygen when the combustion of the filings, as they fell into the oxygen, became almost insupportably brilliant. You will see how wonderfully different the effect is in the jar, because there we have oxygen instead of common air. End of section 6.
Section 7 on the various forces of nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Michelle Fry, Baton Rouge, Louisiana, in June 2021. On the various forces of nature by Michael Faraday. Section 7. Lecture 4, Chemical Affinity, Heat. We shall have to pay a little more attention to the forces existing in water before we can have a clear idea on the subject. Besides the attraction which there is between its particles to make it hold together as a liquid or a solid, there is also another force, different from the former, one which yesterday, by means of the voltaic battery, we overcame, drawing from the water two different substances, which, when heated by means of the electric spark, attracted each other and rushed into combination to reproduce water. Now I propose today to continue this subject and trace the various phenomena of chemical affinity. And for this purpose, as we yesterday considered the character of oxygen, of which I have here 2 jars, oxygen being those particles derived from the water which enable other bodies to burn, we will now consider the other constituent of water. And without embarrassing you too much with the way in which these things are made, I will proceed now to show you our common way of making hydrogen. I called it hydrogen yesterday. It is so called because it helps to generate water. I put into this retort some zinc, water, and oil of vitriol, and immediately an action takes place which produces an abundant evolution of gas, now coming over into this jar and bubbling up in appearance exactly like the oxygen we obtained yesterday. The processes, you see, are very different, though the result is the same, insofar as it gives us certain gaseous particles. Here, then, is the hydrogen.
how the force of heat affects chemical affinity, and so forth, but we must try and comprehend what relation they bear to each other, and how these powers might be changed one into the other. And it will today require all my care, and all your care too, to make this clear to your minds. I shall be obliged to confine myself to one or two instances, because to take in the whole extent of this mutual relation and conversion of forces would surpass the human intellect. In the first place, then, here is a piece of fine zinc foil, and if I cut it into narrow strips and apply it to the power of heat, admitting the contact of air at the same time, you will find that it burns. And then, seeing that it burns, you will be prepared to say that there is chemical action taking place. You see, all I have to do is to hold the piece of zinc at the side of the flame, so as to let it get heated, and yet to allow the air, which is flowing into the flame from all sides, to have access to it. There is the piece of zinc burning just like a piece of wood, only brighter. A part of the zinc is going up into the air in the form of that white smoke, and part is falling down onto the table. This, then, is the action of chemical affinity exerted between the zinc and the oxygen of the air. I will show you what a curious kind of affinity this is by an experiment, which is rather striking when seen for the first time. I have here some iron filings and gunpowder, and will mix them carefully together with as little rough handling as possible. Now we will compare the combustibility, so to speak, of the two. I will pour some spirit of wine into a basin and set it on fire. And having our flame, I will drop this mixture of iron filings and gunpowder through it, so that both sets of particles will have an equal chance of burning. And now, tell me, which of them is it that burns? You see a plentiful combustion of the iron filings, but I want you to observe that, though they have equal chances of burning, we shall find that by far the greater part of the gunpowder remains untouched. I have only to drain off this spirit of wine and let the powder, which has gone through the flame, dry, which it will do in a few minutes, and I will then test it with a lighted match. So ready is the iron to burn that it takes, under certain circumstances, even less time to catch fire than gunpowder. As soon as the gunpowder was dry, Mr. Anderson handed it to the lecturer, who applied a lighted match to it, when a sudden flash showed how large a proportion of the gunpowder had escaped combustion when falling through the flame of alcohol. These are all cases of chemical affinity, and I show them to make you understand that we are about to enter upon the consideration of a strange kind of chemical affinity, and then to see how far we are enabled to convert this force of affinity into electricity or magnetism, or any other of the forces which we have discussed. Here is some zinc. I keep to the metal zinc, as it is very useful for our purpose. And I can produce hydrogen gas by putting the zinc and sulfuric acid together, as they are in that retort. There you see the mixture which gives us hydrogen. The zinc is pulling the water to pieces and setting free hydrogen gas. Now, we have learned by experience that if a little mercury is spread over that zinc, it does not take away its power of decomposing the water, but modifies it most curiously. See how that mixture is now boiling? But when I add a little mercury to it, the gas ceases to come off. We have now scarcely a bubble of hydrogen set free, so that the action is suspended for the time. We have not destroyed the power of chemical affinity, but modified it in a wonderful and beautiful manner. Here are some pieces of zinc covered with mercury, exactly in the same way as the zinc in that retort is covered. If I put this plate into sulfuric acid, I get no gas. But this most extraordinary thing occurs, that if I introduce, along with the zinc, another metal which is not so combustible, then I reproduce all the action. I'm now going to put to the amalgamated zinc, in this retort, some portions of copper wire, the copper being not so combustible a metal as the zinc, and observe how I get hydrogen again. As in the first instance, there the bubbles are coming over through the pneumatic trough and ascending faster and faster in the jar. The zinc is now acting by reason of its contact with the copper. Every step we are now taking brings us to a knowledge of new phenomena. That hydrogen which you now see coming off so abundantly does not come from the zinc as it did before, but from the copper. Here is a jar containing a solution of copper. If I put a piece of this amalgamated zinc into it and leave it there, it has scarcely any action. And here is a plate of platinum, which I will immerse in the same solution, and might leave it there for hours, days, months, or even years, and no action would take place. But by putting them both together and allowing them to touch, you will see what a coating of copper there is immediately thrown down on the platinum. Why is this? The platinum has no power of itself to reduce the metal from that fluid, but it has in some mysterious way received this power by its contact with the metal zinc. Here then, you see a strange transfer of chemical force from one metal to another. The chemical force from the zinc is transferred and made over to the platinum by the mere association of the two metals. I might take, instead of the platinum, a piece of copper or of silver, and it would have no action of its own on this solution. But the moment the zinc was introduced and touched the other metal, then the action would take place, and it would become covered with copper. Now, is this not most wonderful and beautiful to see? We still have the identical chemical force of the particles of zinc acting, and yet, in some strange manner, we have the power to make that chemical force, or something it produces, travel from one place to another. For we do make the chemical force travel from the zinc to the platinum by this very curious experiment of using the two metals in the same fluid in contact with each other. Let us now examine these phenomena a little more closely. Here is a drawing in which I have represented a vessel containing the acid liquid and the slips of zinc and platinum or copper, and I have shown them touching each other outside by means of a wire coming from each of them. For it matters not whether they touch in the fluid or outside by pieces of metal attached. They still, by that communication between them, have this power transferred from one to another. Now, if instead of only using one vessel, as I have shown there, I take another, and put in zinc and platinum, zinc and platinum, zinc and platinum, and connect the platinum of one vessel with the zinc of another, the platinum of this vessel with the zinc of that, and so on, we should only be using a series of these vessels instead of one. This we have done in that arrangement which you see behind me. I am using what we call a Groves voltaic battery, in which one metal is zinc and the other platinum, and I have as many as 40 pairs of these plates, all exercising their force at once in sending the whole amount of chemical power there evolved through these wires under the floor and up to these two rods coming through the table. We need do no more than just bring these two ends in contact, and the spark shows us what power is present. And what a strange thing it is to see that this force is brought away from the battery behind me and carried along through these wires. I have here an apparatus which Sir Humphrey Davy constructed many years ago in order to see whether this power from the voltaic battery caused bodies to attract each other in the same manner as the ordinary electricity did. He made it in order to experiment with his large voltaic battery, which was the most powerful then in existence. You will see there are in this glass jar 2 leaves of gold, which I can cause to move to and fro by this rackwork. I will connect each of these gold leaves with separate ends of this battery, and if I have a sufficient number of plates in the battery, I shall be able to show you that there will be some attraction between those leaves, even before they come in contact. If I bring them sufficiently near when they are in communication with the ends of the battery, they will be drawn gently together, and you will know when this takes place, because the power will cause the gold leaves to burn away, which they could only do when they touched each other. Now, I am going to cause these 2 leaves of gold to approach gradually, and I have no doubt that some of you will see that they approach before they burn, and those who are too far off to see them approach will see by their burning that they have come together. Now they are attracting each other long before the connection is complete, and there they go, burnt up in that brilliant flash. So strong is the force. You see, from the attractive force at the 2 ends of this battery, that these are really and truly electrical phenomena. Now let us consider what is this spark. I take these 2 ends and bring them together, and there I get this glorious spark, like the sunlight in the heavens above us. What is this? It is the same thing that you saw when I discharged the large electrical machine, when you saw but one single bright flash. It is the same thing, only continued, because here we have a more effective arrangement. Instead of having a machine which we are obliged to turn for a long time together, we have here a chemical power which sends forth the spark. And it is wonderful and beautiful to see how this spark is carried about through these wires. I want you to perceive, if possible, that this very spark and the heat it produces, for there is heat, is neither more nor less than the chemical force of the zinc, its very force carried along wires and conveyed to this place. I'm about to take a portion of the zinc and burn it in oxygen gas, for the sake of showing you the kind of light produced by the actual combustion in oxygen gas of some of this metal. A tassel of zinc foil was ignited at the spirit lamp and introduced into a jar of oxygen when it burnt with a brilliant light. That shows you what the affinity is when we come to consider it in its energy and power. And the zinc is being burned in the battery behind me at a much more rapid rate than you see in that jar, because the zinc is there dissolving and burning, and produces here this great electric light. That very same power which in that jar you saw evolved from the actual combustion of the zinc in oxygen is carried along these wires and made evident here. And you may, if you please, consider that the zinc is burning in those cells, and that this is the light of that burning, bringing the two poles in contact and showing the electric light. And we might so arrange our apparatus as to show that the amounts of power evolved in either case are identical. Having thus obtained power over the chemical force, how wonderfully we are able to convey it from place to place. When we use gunpowder for explosive purposes, we can send into the mine chemical affinity by means of this electricity. Not having provided fire beforehand, we can send it in at the moment we require it. Now here is a vessel containing 2 charcoal points, and I bring it forward as an illustration of the wonderful power of conveying this force from place to place. I have merely to connect these by means of wires to the opposite ends of the battery and bring the points in contact. See what an exhibition of force we have. We have exhausted the air so that the charcoal cannot burn, and therefore the light you see is really the burning of the zinc in the cells behind me. There is no disappearance of the carbon, although we have that glorious electric light, and the moment I cut off the connection, it stops. Here is a better instance to enable some of you to see the certainty with which we can convey this force, where, under ordinary circumstances, chemical affinity would not act. We may absolutely take these 2 charcoal poles down underwater and get our electric light there. There they are in the water, and you observe, when I bring them into connection, we have the same light as we had in that glass vessel. Now, besides this production of light, we have all the other effects and powers of burning zinc. I have a few wires here which are not combustible, and I'm going to take one of them, a small platinum wire, and suspend it between these 2 rods which are connected with the battery. And when contact is made at the battery, see what heat we get. Is not that beautiful? It is a complete bridge of power. There is metallic connection all the way around in this arrangement, and where I have inserted the platinum, which offers some resistance to the passage of the force, you see what an amount of heat is evolved. This is the heat which the zinc would give if burnt in oxygen, but as it is being burnt in the voltaic battery, it is giving it out at this spot. I will now shorten this wire, that the shorter the obstructing wire is, the more and more intense is the heat, until at last our platinum is fused and falls down, breaking off the circuit. Here is another instance. I will take a piece of the metal silver and place it on charcoal connected with one end of the battery, and lower the other charcoal pole onto it. See how brilliantly it burns? Here is a piece of iron on the charcoal. See what a combustion is going on, and we might go on in this way, burning almost everything we place between the poles. Now, I want to show you that this power is still chemical affinity, that if we call the power which is evolved at this point heat, or electricity, or any other name referring to its source, or the way in which it travels, we still shall find it to be chemical action. Here is the colored liquid which can show by its change of color the effects of chemical action. I will pour part of it onto this glass, and you will find that these wires have a very strong action. I'm not going to show you any effects of combustion or heat, but I will take these two platinum plates and fasten one to the one pole and the other to the other end, and place them in this solution, and in a very short time, you will see the blue color will be entirely destroyed. See, it is colorless now. I have merely brought the end of the wires into the solution of indigo, and the power of electricity has come through these wires and made itself evident by its chemical action. There's also another curious thing to be noticed. Now we are dealing with the chemistry of electricity, which is that the chemical power which destroys the color is only due to the action on one side. I will pour some more of this sulfo-indigotic acid into a flat dish, and will then make a porous dike of sand, separating the two portions of fluid into two parts. And now we shall be able to see whether there is any difference in the two ends of the battery, and which it is that possesses this peculiar action. You see, it is the one on my right hand which has the power of destroying the blue, for the portion on that side is thoroughly bleached, while nothing has apparently occurred on the other side. I say apparently, for you must not imagine that, because you cannot perceive any action, none has taken place. Here we have another instance of chemical action. I take these platinum plates again, and immerse them in this solution of copper, from which we formerly precipitated some of the metal, when the platinum and zinc were both put in it together. You see that these two platinum plates have no chemical action of any kind. They might remain in the solution as long as I liked, without having any power of themselves to reduce the copper. But the moment I bring the two poles of the battery in contact with them, the chemical action, which is there transformed into electricity and carried along the wires, again becomes chemical action at the two platinum poles. And now we shall have the power appearing on the left-hand side and throwing down the copper in a metallic state on the platinum plate. And in this way, I might give you many instances of the extraordinary way in which this chemical action, or electricity, may be carried about. That strange nugget of gold, of which there is a model in the other room, and which has an interest of its own in the natural history of gold, and which came from Ballarat, was worth 8,000 or 9,000 pounds when it was melted down last November, was brought together in the bowels of the earth, perhaps ages and ages ago, by some power as this. And there's also another beautiful result, dependent upon chemical affinity, in that fine lead tree, the lead growing and growing by virtue of this power. The lead and the zinc are combined together in a little voltaic arrangement, in a manner far more important than the powerful one you see here, because in nature, these minute actions are going on forever, and are of great and wonderful importance in the precipitation of metals and the formation of mineral veins, and so forth. These actions are not for a limited time, like my battery here, but they act forever in small degrees. So you see, we have this wire evidently affecting the magnetic needle under these circumstances. Let me show you that a little more strongly. I have here a quantity of wire, which has been wound into a spiral, and this will affect the magnetic needle in a very curious manner, because, owing to its shape, it will act very like a real magnet. The copper spiral has no power over that magnetic needle at present, but if I cause the electric current to circulate through it, by bringing the two ends of the battery in contact with the ends of the wire which forms the spiral, what will happen? Why, one end of the needle is most powerfully drawn to it, and if I take the other end of the needle, it is repelled. So you see, I have produced exactly the same phenomena as I had with the bar magnet, one end attracting and the other repelling. Is not this, then, curious, to see that we can construct a magnet of copper? Furthermore, if I take an iron bar and put it inside the coil, so long as there is no electric current circulating around, it has no attraction, as you will observe if I bring a little iron filings or nails near the iron. But now, if I make contact with the battery, they are attracted at once. It becomes at once a powerful magnet, so much so that I should not wonder if these magnetic needles on different parts of the table pointed to it. And I will show you by another experiment what an attraction it has. This piece and that piece of iron and many other pieces are now strongly attracted to it. But as soon as I break contact, the power is all gone, and they fall. What then can be a better or stronger proof than this of the relation of the powers of magnetism and electricity? Again, here is a little piece of iron which is not yet magnetized. It will not at present take up any of these nails, but I will take a piece of wire and coil it round the iron, the wire being covered with cotton in every part. It does not touch the iron, so that the current must go round in this spiral coil. I am in fact preparing an electromagnet. We are obliged to use such terms to express our meaning because it is a magnet made by electricity, because we produce, by the force of electricity, a magnet of far greater power than a permanent steel one. It is now completed, and I will repeat the experiment which you saw the other day of building up a bridge of iron nails. The contact is now made, and the current is going through. It is now a powerful magnet. Here are the iron nails which we had the other day, and now I have brought this magnet near them. They are clinging so hard that I can scarcely move them with my hand. But when the contact is broken, see how they fall. What can show you better than such an experiment as this, the magnetic attraction from which we have endowed these portions of iron? Here, again, is a fine illustration of this strong power of magnetism. It is a magnet of the same sort as the one you have just seen. I am about to make the current of electricity pass through the wires which are round this iron for the purpose of showing you what powerful effects we get. Here are the poles of the magnet, and let us place on one of them this long bar of iron. You see, as soon as contact is made, how it rises in position. And if I take such a piece of this cylinder and place it on, woe be to me if I get my finger between. I can roll it over, but if I try to pull it off, I might lift up the whole magnet. But I have no power to overcome the magnetic power, which is here evident. I might give you an infinity of illustrations of this high magnetic power. There is that long bar of iron held out, and I have no doubt that, if I were to examine the other end, I should find that it was a magnet. See what power it must have to support not only these nails, but all those lumps of iron hanging on to the end. What then can surpass these evidences of the change of electric force into electricity, and electricity into magnetism? I might show you many other experiments whereby I could obtain electricity and chemical action, heat and light, from a magnet. But what more need I show you to prove the universal correlation of the physical forces of matter and their mutual conversion one into another? And now let us give place, as juveniles, to the respect we owe to our elders. And for a time, let me address myself to those of our seniors who have honored me with their presence during these lectures. I wish to claim this moment for the purpose of tendering our thanks to them, and my thanks to you all for the way in which you have borne the inconvenience that I at first subjected you to. hope that the insight which you have here gained, discovered, may be the occasion of some amongst you turning your attention to these subjects. For what study is there more fitted to the mind of man than that of the physical sciences? And what is there more capable of giving him an insight into the actions of those laws, a knowledge of which gives interest to the most trifling phenomenon of nature? Mind, tongues in trees, books in the running brooks, sermons in stones, and good in everything. End of section 9. Recording by El-Hewie.
Section 10 of On the Various Forces. LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Marvin Benarescu. On the Various Forces of Nature by Michael Faraday. Lighthouse illumination, the electric light. Delivered before the Royal Institution on Friday, 9th of March, 1860. There is no part of my life which gives me more delight than my connection with the Trinity House. The occupation of nations, joined together to guide the mariner over the sea, to all a point of great interest, is infinitely more so to those who are concerned in the operations which they carry into effect, and it certainly has astonished me, since I have been connected with the Trinity House, to see how beautifully and how wonderfully shines forth amongst nations at large the desire to do good, and you will not regret having come here tonight if you follow me in the various attempts which have been made to carry out the great object of guiding in safety all people across the dark and dreary waste of waters. It is wonderful to think how eagerly efforts at improvement are made by the various public bodies, the Trinity House in this country, and commissions in France and other nations, and whilst the improvements progress, we come to the knowledge of such curious difficulties, and such odd modes of getting over those difficulties, as are not easy to be conceived. I must ask you this evening to follow me from the simplest possible method of giving a sign by means of a light to persons at a distance, to the modes at which we have arrived in the present day, and to consider the difficulties which arise when carrying out these improvements to a practical result, and the extraordinary care which those who have to judge on these points must take in order to guard against the too hasty adoption of some fancied improvement, thus, as has happened in some few cases, doing harm instead of good. If I try to make you understand these things partly by old models, and partly by those which we have here, it is only that I may the better be enabled to illustrate that which I look forward to as the higher mode of lighting, by means of the electric lamp and the limelight. There is nothing more simple than a candle being set down in a cottage window to guide a husband to his home. But when we want to make a similar guide on a large scale, not merely over a river or over a moor, but over large expanses of sea, how can we then make the signal using only a candle? I have shown in this diagram what we may imagine to be the rays of a candle or any other source of light, emanating from the center of a sphere in all directions round to infinite distances. After this simple kind of light had been used for some time, it being found to be liable to be obscured by fogs, or distance, or other circumstance, there arose the attempt to make larger lights by means of fires, and after that there was introduced a very important refinement in the mode of dealing with the light, namely, the principle of reflection, for, understand this, which is not known by all, and not known by many who should know it, that when we take a source of light, a single candle, for instance, giving off any quantity of light, we can by no means increase that light. We can make arrangements around and about the light, as you see here, but we can by no means increase the quantity of light. The utmost I can do is to direct the light which the lamp gives me, by taking a certain portion of the rays going off on one side and reflecting them onto the course of the rays which issue in the opposite direction. First of all, let us consider how we may gather in the rays of light which pass off from this candle. you will easily see that if I could take the half rays on the one side and could send them by any contrivance over to the other side, I should gain an advantage in light on the side to which I direct them. This is effected in a beautiful manner by the parabolic mirror, by means of which I gather all that portion of the rays which are included in it, upwards, downwards, sideways, anywhere within its sphere of action. They are all picked up and sent forward. You thus see what a beautiful and important invention is that of the parabolic reflector for throwing forward the rays of light. Before I go further into the subject of reflection, let me point out a further mode of dealing with the direction of the light. For instance, here is a candle, and I can employ the principle of refraction to bend and direct the rays of light. And if I want to increase the light in any one direction, I must either take a reflector or use the principle of refraction. I will place this lens in front of the candle, and you will easily see that by its means I can throw onto that sheet of paper a great light. That is to say, that instead of the light being thrown all about, it is refracted and concentrated onto that paper. So here I have another means of bending the light and sending it in one direction. And you see above a still better arrangement for the same purpose, one which comes up to the maximum, I may say, of the ability of directing light by this means. You are aware that without that arrangement of glass, the light would be dispersed in all directions, but the lens being there, all the light which passes through it is thrown into parallel beams and cast horizontally along. There is consequently no loss of light. The beam goes forward of the same dimensions, and will consequently continue to go forward for 5 or 10 miles, or so long as the imperfection of the atmosphere does not absorb it. And see, what a glorious power that is, to be able to convert what was just
darkness on that paper into brilliant light. Whenever we have refraction of this sort, we are liable to an evil consequence upon the necessary imperfections in the form of the lens, and Dr. Tyndall will take this lens and will show you even in the small and perfect apparatus what is the evil of spherical aberration with which we have to fight. This can be illustrated by means of the electric lamp. If you look at the screen, you will see produced by means of this lens a figure of the coal points. This image is produced by the rays which pass through the middle of the lens, a piece of card with a hole in the centre being placed in front. But if, keeping the rest of the apparatus in the same position, I change this card for another piece which will only allow the rays to pass through the edge of the lens, you observe how inferior the image will be. In order to get it distinct, I have to bring the screen much nearer the lamp, and so, if I take the card away altogether and allow the light to pass through all parts of the lens, we cannot get a perfect image, because the different parts of the lens are not able to act together. This spherical aberration is, therefore, what we try to avoid by building up compound lenses in the manner here shown. Look at this beautiful apparatus. Is it not a most charming piece of workmanship? Before first, and Fresnel afterwards, built up these kinds of lenses, ring with a ring, each at its proper adjustment, to compensate for the effects of spherical aberration. The ring-rounded centre lens is ground so as to obviate what would otherwise give rise to spherical aberration, and the next ring being corrected in the same manner, you will perceive, if you look at the disc of light thrown by the apparatus upstairs, that there is nothing like the amount of aberration that there would have been if it had been one great bull's-eye. Here is one of Fresnel's lamps of the fourth order so constructed. Observe the fine effect obtained by these different lenses, as you see them revolved before you, and understand that all this upper part is made to form part of the lens, each prism throwing its rays to increase the effect, and although you may think it is imperfect, because if you happen to sit below or above the horizontal line, you perceive but little of any of the light, yet you must bear in mind that we want the rays to go in a straight line to the horizon, so that all the building up of rings of glass is for the purpose of producing one fine glorious lens of large size to send the rays all in one direction. Here is another apparatus used to pull the rays down to a horizontal sheet of light, so that the mariner may see it as a constant and uniform fixed light. The former lamp is a revolving one, and the light is seen only at certain times, as the lenses move round, and these are the points which make them valuable in their application. There are various orders and sizes of lights in lighthouses, to shine for 20 or 30 miles over the sea, and to give indications according to the purposes for which they are required. But suppose we want more effect than is produced by these means, how are we to get more light? Here comes the difficulty. We cannot get more light, because we are limited by the condition of the burner. In any of these cases, if the spreading of the ray, or divergence, as it is called, is not restrained, it soon fails from weakness, and if it does not diverge at all, it makes the light so small that perhaps only 1 in 100 can see it at the same time. The South Foreland lighthouse is, I think, 300 or 400 feet above the level of the sea, and therefore it is necessary to have a certain divergence of the beam of light, in order that it may shine along the sea to the horizon. I have drawn here 2 wedges. One has an angle of 15 degrees, and shows you the manner in which the light opens out from this reflector, seen at the distance of half a mile or more. The other wedge has an angle of 6 degrees, which is the beautiful angle of Fresnel. When the angle is less than 6 degrees, the mariner is not quite sure that he will see the light. He may be beneath or above it, and in practice it is found that we cannot have a larger angle of 15 degrees, or a less one than 6 degrees. In order, therefore, to get more light, we must have more combustion, more cotton, more oil. But already there are in that lamp 4 wicks put in concentric rings, one within the other, and we cannot increase them much more, owing to the divergence which would be caused by an increase in the size of the light. The more the divergence, the more the light is diffused and lost. We are therefore restrained by the condition of the light and the apparatus to a certain size lamp. At Teignmouth, some of the revolving lights have 10 lamps and reflectors, all throwing their light forward at once. But even with 10 lamps and reflectors, we do not get sufficient light, and we want therefore the means of getting light more intense than a candle in the space of the candle. Not merely an accumulation of candle upon candle, but a concentration into the space of the candle of a greater amount of light, and it is here that the electric light comes to be of so much value. Let me now show you what are the properties of that light which make it useful for lighthouse illumination, and which has been brought to a practical condition by the energy and constancy of Professor Holmes. I will first image of the charcoal points on the screen and draw your attention to the spot where the light is produced. There are the coal points. The two carbons are brought within a certain distance. The electricity is being urged across by the voltaic battery, and the coal points are brought into an intense state of ignition. You'll observe that the light is essentially given by the carbons. You see that one is much more luminous than the other, and that is the end which principally forms the spark. The other does not shine so much, and there is a space between the two, which, although not very luminous, is most important to the production of the light. Dr. Tyndall will help me in showing you that a blast of wind will blow out that light. The electric light can in fact be blown out easier than a candle. We have the power of getting our light where we please. If I cause the electricity to pass between carbon and mercury, I get a most intense and beautiful light, most of it being given off from the portion of the mercury between the liquid and the solid coal. I can show you that the light is sometimes produced by the vapor between the two coals better if I take silver than when I use mercury. Here is the carbon coal. There is the silver, and there is the beautiful green light, which comes from the intervening portions. Now, that light is more easily blown out than the common lamp, the slightest puff of wind being sufficient to extinguish it, as you will see if Dr. Tyndall brings upon it. You see, therefore, how we are able by using this electric spark to get, first of all, the light into a very small space. That oil lamp has a burner of 3 3/4 inches in diameter. Compare the size of the flame with the space occupied by this electric light. Next, compare the intensity of this light with any other. If I take this candle and place it by the side, I actually seem to put out the candle. We are thus able to get a light which, while it surpasses all others in brilliancy, is at the same time not too large, for I might put this light into an apparatus not larger than a hat, and yet I could count upon the rays being useful. Moreover, when such large burners are used in a lantern, we have to consider whether the bars of the window do not interfere, to throw a shadow or otherwise. But with this light, there will be no difficulty of that sort, as a single small speculum, no larger than a hat, will send it in any direction we please, and it is wonderful what advantages, by reason of its small bulk, we have in the consideration of the different kinds of apparatus required, reflecting or refracting, irrespective of other reasons for using the electric light. And it is these kinds of things which make us decide most earnestly and carefully in favour of the electric light. I am going to show you the effect that will take place with that large lens when we throw the oil lamp out of action and put the electric light into use. It is astonishing to find how little the eye can compare the relative intensities of two lights. Look at that screen and try to recollect the amount of light thrown upon it from the 3 3/4 inch lamp of Fresnel. And now, when we shift the lens sideways, look at the glorious light arising from that small carbon point. See how beautifully it shines in the focus of that lens and throws the rays forward. At present, the electric light is put at just the same distance as the oil light, and therefore, being in the focus of the lens, we have parallel rays which are thrown forward in a perfectly straight line, as you will see by comparing the size of the lens with that of the light thrown on the screen. You will now see how far we can affect this beam of light by increasing or diminishing the distance of the lamp. We are able, by a small adjustment, to get a beam of a large or small angle, and observe what power I have now over it. For if I want to increase the degrees of divergence, I am limited by the power of light, in the case of the oil lamp. But with the electric light, I can make it spread over any width of the horizon by this simple adjustment. These, then, are some of the reasons which make it desirable to employ the electric light. By means of a magnet and of motion, we can get the same kind of electricity as I have here from the battery, and, under the authority of the Trinity House, Professor Holmes has been occupied in introducing the magnetoelectric light in the lighthouse at the South Foreland. For the voltaic battery has been tried under every conceivable circumstance, and, I take the liberty of saying, it has hitherto proved a decided failure. Here, however, is an instrument wrought only by mechanical motion. The moment we give motion to the soft iron in front of the magnet, we get a spark. It is true, in this apparatus it is very small, but it is sufficient for you to judge of its character. It is the magnetoelectric light, and an instrument has been constructed, as there shown, which represents a number of magnets placed radially upon a wheel, 3 wheels of magnets and 2 sets of helices. When the machine, which is worked by a 2 horsepower engine, is properly set in motion, and the different currents are all brought together and thrown by Professor Holmes up into the lantern, we have a light equal to the one we have been using this evening. For the last 6 months, the South Foreland has been shining by means of this electric light, beyond all comparison, better than its former light. It has shone into France and has been seen there and taken notice of by the authorities, who work with beautiful accord with us in all these matters. Never for once during 6 months has it failed in doing its duty, never once, more than was expected by the inventor. It has shone forth with its own peculiar character, and this even with the old apparatus, for, as yet, no attempt has been made to construct special reflectors or refractors for it, because it is not yet established. I will not tell you that the problem of employing the magnetoelectric spark for lighthouse illumination is quite solved yet, although I desire it should be established most earnestly, for I regard this magnetic spark as one of my own offspring. The thing is not yet decidedly accomplished, and what the considerations of expense and other matters may be, I cannot tell. I am only here to tell you as a philosopher how far the results have been carried, but I do hope that the authorities will find it a proper thing to carry out in full. If it cannot be introduced at all the lighthouses, if it can only be used at one, why, really, it will be an honour to the nation which can originate such an improvement as this, one which must of necessity be followed by other nations. You may ask, what is the use of this bright light? It would not be useful to us, were it not for the constant changes which are taking place in the atmosphere, which is never pure. Even when we can see the stars clearly on a bright night, it is not a pure atmosphere. The light of a lighthouse, more than any other, is liable to be dimmed by vapours and fogs, and where we most want this great power is not in the finest condition of the atmosphere, but when the mariner is in danger, when the sleet and rain are falling, and the fogs arise, and the winds are blowing, and he is nearing coasts where the water is shallow and abounds with rocks. Then is his time of danger, when he most wants this light. I am going to show you how, by means of a little steam, I can completely obscure this glorious sun, this electric light which you see. The cloud now obscuring the light on the screen is only such a cloud as you see when sitting in a train on a fine summer's day. You may observe that the vapour passing out of the funnel casts as deep a shadow on the ground as the black funnel. The very sun itself is extinguished by the steam from the funnel, so that it cannot give any light, and the sun itself, if set in the lighthouse, would not be able to penetrate such a vapour. Now, the haze of this cloud of steam is just what we have to overcome, and the electric light is as soon, proportionally, extinguished by an obstruction of this kind as any other light. Lights, one 4 times the intensity of the other, and we extinguish half of one by a vapour, we extinguish half of the other, and that is a fact which cannot be set aside by any arrangement. But, then, we fall back upon the amount of light, which the electric spark does give us an aid of the power of penetrating the fog, for the light of the electric spark shines so far at times, that even before it has arisen above the horizon, 25 miles off, it can be seen. This intense light has, therefore, that power which we can take advantage of bearing a great deal of obstruction, before it is entirely obscured by fogs or otherwise. Taking care that we do not lead our authorities into error by the advice given, we hope that we shall soon be able to recommend the Trinity House, from what has passed, to establish either one or more good electric lights in this country. Section 11. On the various forces of nature. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. On the various forces of nature, by Michael Faraday. Lecture notes. Lecture 1. Note 1. Page 13. The opening lecture was twice postponed on account of Dr. Faraday's illness. 2. Page 22. Platinum, with one exception, the heaviest body known, is 21.5 times heavier than water. 3. Page 22. Aluminum is 2.5 times heavier than water. 4. Pages 23 and 24. Power or property in water. This power, the heat by which the water is kept in a fluid state, is said under ordinary circumstances to be latent or insensible. When, however, the water changes its form, and by uniting with a lime or sulfate of copper, becomes solid. The heat which retained it in liquid state is evolved. 5. Page 23. Anhydrous sulfate of copper. Sulfate of copper deprived of its order of crystallization. To obtain it, the blue sulfate is calcium in earthen crucible. 6. Page 29. Add a little liquid to the marble and decompose it. Marble is composed of a carbonic acid and lime, and in chemical language is called carbonate of lime. When sulfuric acid is added to it, the carbonic acid is set free. The sulfuric acid unites with the lime to form sulfate of lime. Carbonic acid, under ordinary circumstances, is a colorless, invisible gas, not half as heavy again as air. Dr. Faraday first showed that under great pressure, it could be obtained in a liquid state. Laurier, French chemist, afterwards found that it could be solidified. Lecture 2. Note 7, page 55. Crystallization of alum. The solution must be saturated. That is, it must contain as much alum as can possibly be dissolved. In making the solution, it is best to add powdered alum to hot water as long as it dissolves, and when no more is taken up, allow the solution to stand a few minutes, then pour it off from the dirt and undissolved alum. 8. Page 57. Red precipitate of iodide, mercury. A little care is necessary to obtain this precipitate. The solution of potassium should be added to the solution of perchlorate of mercury, corrosive subtly, very gradually. The red precipitate which first falls is redissolved in the liquid stirred. When a little more of the iodide of potassium is added, a pale red precipitate is formed, which, on further addition of the iodide, changes into brilliant scarlet fine iodide of mercury. If too much iodide of potassium is added, the scarlet precipitate disappears, and the colorless solution is added. 9. Page 57. Paper coated with scarlet fine iodide of mercury. In order to fix the fine iodide on paper, it must be mixed with a little weak gum water, and then spread over the paper, which must be dried without heat. Fine iodide of mercury is said to be dimorphous, that is, able to assume two different forms. 10. Page
exam room, building a comprehensive health picture. And the first thing that we're going to do when we have you in the room is we're going to draw your blood. And generally a lot of our members come to us and say, hey, I have to wait usually 3 to 5 days, maybe a week for my blood work to come back. And that's when we thought, why don't we just build a blood processing lab on site? It takes 12 minutes for blood work to come back. And what we do to make for a very clean, easy experience is we use what we call an infrared main mount. Check this out.
Oscillate the same frequency that the blades of the fan were casting shadows over the crystal. One of Old's colleagues immediately realized that the ingot had a crack in it that formed a natural junction. And this tiny natural junction in an otherwise solid block was acting just like the much more delicate junction between the end of a wire and a crystal that most had discovered. Except here, it was sensitive to light. The ingot had cracked because either side contained slightly different amounts of impurities. One side had slightly more of the element phosphorus, while the other had slightly more of a different impurity, boron. And electrons seemed to be able to move across from the phosphorus side to the boron side, but not vice versa. Photons of light shining down onto the crystal were knocking electrons out of the atoms, but it was the impurity atoms that were driving this flow. Phosphorus has an electron that is going spare, and boron is keen to accept another. So electrons tended to flow from the phosphorus side to the boron side, and crucially only flowed one way across the junction. The head of the semiconductor team, William Shockley, saw the potential of this one-way junction within a crystal. But how would it be possible to create a crystal with 2 junctions in it that could be used as an amplifier? Another researcher at Bell Labs called Gordon Teal had been working on a technique that would allow just that. He discovered a special way to grow single crystals of the semiconductor germanium. In this research institute, they grow semiconductor crystals the same way that Teal did back in Bell Labs. But in here, they grow them much, much bigger. At the bottom of this vat is a container with glowing hot molten germanium, just as pure as you can get it. Inside it are a few atoms of whatever impurity is required to alter its conductive properties. Now, the rotating arm above has a seed crystal at the bottom that has been dipped into the liquid and will be slowly raised up again. As the germanium cools and hardens, it forms a long crystal like an icicle below the seed. The whole length is one single beautiful germanium crystal. Teal worked out that as the crystal is growing, other impurities can be added to the vat and mixed in. This gives us a single crystal with...
Elton, I want you bringing the thunder to this next hill. Back to the incline right now. 60 seconds from love, baby, let's go.
1, 2, 1, 2. Taking the pulse, baby. By now, you should be feeling real toasty. Keep going.
The most
3, 2,
demanding
1, and we're done.
trying time in my life.
I told you we'd have
And
fun
then
today,
on the
Peloton.
phone you said that time was mine.
Is your network slow and underperforming? Does your IT support take forever? No need to panic. At Platte River Networks, we've created Intuition, a robust management solution that'll help your company improve IT performance from the server infrastructure to the desktop and everything in between. Full design, Build, monitor, manage, maintain, and constantly improve your technology network. Plus, we do not outsource and become part of your team. To learn more, contact us today.
Thin layers of different impurities, creating junctions within the crystal. This crystal with two junctions in it was Shocky's dream. Applying a small current through the very thin middle section allows a much larger current to flow through the whole triple sample. From a single crystal like this, hundreds of tiny solid blocks could be cut, each containing the two junctions that would allow the movement of electrons through them to be precisely controlled. 18th century, where our story begins. This is the Royal Society in London. In the early 1700s, after years in the wilderness, Isaac Newton finally took control of it after the death of his arch-enemy, Robert Hooke. Newton brought in his own people to the key jobs to help shore up his new position. The new head of demonstrations there was 35-year-old Francis Hawksby. Notes from the Royal Society in 1705 reveal how hard Hawksby tried to stamp his personality on his weekly meetings, producing ever more spectacular experiments to impress his masters. In November, he came up with this, a rotating glass sphere. He was able to remove the air from inside it using a new machine, the air pump. On his machine, a hand allowed him to spin the sphere. One by one, the candles in the room put out. And Francis placed his hand against the sphere. The audience were about to see something amazing. Inside the glass sphere, a strange ethereal light began to form, dancing around his hand. A light no one had ever seen before. Oh, that's fantastic. You see the beautiful blue glow just marking out the shape of my hands, but then going right round the wall. There's only something alive there. It's difficult to really understand why this dancing blue light meant so much. But we have to bear in mind that at the time, natural phenomena like this was seen to be the work of the Almighty.
This was still a period when, even in Isaac Newton's theory, God was constantly intervening in the conduct of the world. And so it made sense for a lot of people to interpret natural phenomena as acts of God.
So when a mere mortal meddled with God's work, it was almost beyond rational comprehension. Hawksby never realized the full significance of his experiment. He lost interest in his glowing sphere and spent the last few years of his life building ever more spectacular experiments for Isaac Newton to test his other theories. He never realized that he'd unwittingly started an electrical revolution. Before Hawksby, electricity had been merely a curiosity. The ancient Greeks rubbed amber, which they called electron, to get small shocks. And even Queen Elizabeth I marvelled at static electricity's power to lift feathers. But now, Hawksby's machine could make electricity at the turn of a handle, and you could see it. And perhaps even more importantly, his invention coincided with the birth of a new movement sweeping across Europe, called the Enlightenment.
enlightened intellectuals used reason to question the world, and their legacy was radical politics, iconoclastic art, and natural philosophy, or science. But ironically, Hawksby's new machine wasn't immediately embraced by most of these intellectuals, but instead by conjurers and street magicians. And those with an interest in electricity called themselves electricians. One story tells of a dinner party attended by an Austrian count. The electrician had placed some feathers on the table and then charged up a glass rod with a silk handkerchief. He then astonished the guests by lifting up the feathers with the rod. He then went on to charge himself up using one of Hawksby's electrical machines and gave the guests electric shocks, presumably to squeals of delight. But for his pièce de résistance, he placed a glass of cognac in the centre of the table, charged himself up again, and lit it with a spark from the tip of his finger.
There was a trick called the electrical beatification, in which the victim sits on an insulated chair, and above his head hangs a metal crown that doesn't quite touch his head. And then if the crown is electrified, then you get an electric discharge around the crown that looks exactly like a halo, which is why it's called the electric beatification.
As England and the rest of Europe went electricity crazy, the spectacles grew bigger, and the more curious electricians started to ask more profound questions. Not only how can we make our shows bigger and better, but how can we control this amazing power? And for some, can this incredible electrical fire do more than just entertain? One of the first early breakthroughs would never have happened had it not been for a terrible accident. This is Charterhouse in the centre of London. Over the past 400 years, it's been a charitable home for young orphans and elderly gentlemen. And sometime in the 1720s, it also became home to one Stephen Gray. Stephen Gray had been a successful silk dyer from Canterbury. He was used to seeing electric sparks leap from the silk, and they fascinated him. Unfortunately, a crippling accident ended his career and left him destitute. But then he was offered a new life here at Charterhouse, and with it, the time to perform his own electrical experiments. Here at Charterhouse, possibly in this very room, the Great Chamber, Stephen Gray built a wooden frame. From the top beam, he suspended 2 swings using silk rope. He also had a device like this, a Hawksby machine, for generating static electricity. Now, with a large audience in attendance, he got one of the orphan boys who lived here at Charterhouse to lie across the 2 swings. Gray placed some gold leaf in front of him. He then generated electricity and charged the boy through a connecting rod. Gold leaf, even feathers, leapt to the boy's fingers. Some of the audience claimed they could even see sparks flying out from his fingertips. Show business indeed. But to the curious and inquiring mind of Stephen Gray, this said something else as well. Electricity could move. From the machine to the boy's body, through to his hands. But the silk rope stopped it dead. It meant the mysterious electrical fluid could flow through some things, but not through others. It led Gray to divide the world into two different kinds of substances. He called them insulators and conductors. Insulators held electric charge within them and wouldn't let it move, like the silk, or hair, glass, and resin, whereas conductors allowed electricity to flow through them, like the buoy, or metals. It's a distinction which is still crucial even today. Just think of these electric pylons. They work on the same principle that Gray deduced nearly 300 years ago. The wires are conductors. The glass and ceramic objects between the wire and the metal of the pylon are insulators that stop the electricity leaking from the wires into the pylon and down to the earth. They're just like the silk ropes in Gray's experiment. Back in the 1730s, Gray's experiment may have astounded all who saw it, but it had a frustrating drawback. Try as he might, Gray couldn't contain the electricity he was generating for long. It leapt from the machine to the buoy and was quickly gone. The next step in our story came when we learnt how to store electricity. But that would take place not in Britain, but across the Channel in mainland Europe. Across the Channel, electricians were just as busy as their British counterparts, and one centre for electrical research was here in Leiden, Holland. And it was here that a professor came up with an invention that many still regard as the most significant of the 18th century, one that, in some form or another, can still be found in almost every electrical device today. That professor was Pieter van Musschenbroek. Unlike Hawksby and Gray, Musschenbroek was born into academia. But ironically enough, his breakthrough came not because of his rigorous science, but because of a simple human mistake. He was trying to find a way to store electrical charge ready for his demonstrations, and you could almost hear his train of thought as he tries to figure this out. If electricity is a fluid that flows a bit like water, then maybe you can store it in the same way that you can store water. So Musschenbroek went to his laboratory to try to make a device to store electricity. Musschenbroek started to think literally. He took a glass jar and poured in some water. He then placed inside it a length of conducting wire, which was connected at the top to a Hawksby electric machine. Then he put the jar on an insulator to help keep the charge in the jar. He then tried to pour the electricity into the jar, produced by the machine, via the wire, down through into the water. But whatever he tried, the charge just wouldn't stay in the jar. Then one day, by accident, he forgot to put the jar on the insulator, but charged it instead while it was still in his hand. Finally, holding the jar with one hand, he touched the top with the other and received such a powerful electric shock he was almost thrown to the ground. He writes, "It's a new but terrible experiment which I advise you never to try. Nor would I, who've experienced it and survived by the grace of God, do it again for all the Kingdom of France. So I'm going to heed his advice, not touch the top, but instead see if I can get a spark off of it." The sheer power of the electricity which flew from the jar was greater than any seen before. And even more surprisingly, the jar could store that electricity for hours, even days. So in honor of the city where Muschenbroek made his discovery, they called it the Leyden jar. And its fame swept across the world.
And very rapidly from 1745 through the rest of the 1740s, the news of this, it's called the Leyden jar, goes global. It spreads from Japan in East Asia to Philadelphia in Eastern America. It became one of the first quick, globalized scientific news items.
But although the Leyden jar became a global electrical phenomenon, no one had the slightest idea how it worked.
You have a jar of electric fluid, and it turns out that you get a bigger shock from the jar if you allow the electric fluid to drain away to the earth. Why is the shock bigger if the jar's leaking? Why isn't the shock bigger if you make sure that all the electric fluid stays inside the jar? That was how mid-18th century electrical philosophers were faced with this challenge.
Electricity was without doubt a fantastical wonder. It could shock and spark. It could now be stored and moved around. Yet what electricity was, how it worked, and why it did all these things was nothing less than a complete mystery. Within 10 years, a new breakthrough was to come from an unexpected quarter, from a man politically and philosophically at war with the London establishment. And even more shockingly for the British electrical elite, that man was merely a colonial, an American. This painting of Benjamin Franklin hangs here at the Royal Society in London. Franklin was a passionate supporter of American emancipation and saw the pursuit of rational science, and particularly electricity, as a way of rolling back ignorance, false idols, and ultimately his intellectually elitist colonial masters.
And this is mixed with a profoundly egalitarian democratic idea that Franklin and his allies had, which is this is a phenomenon open to everyone. Here's something that the elite doesn't really understand, and we might be able to understand. Here's something that the elite can't control, but we might be able to control. And here's something above all, which is the source of superstition. And we, rational, egalitarian, potentially democratic intellectuals, we will be able to reason it out. It's a magical mystery.
So Franklin decided to use the power of reason to rationally explain what many considered a magical phenomenon, lightning. This is probably one of the most famous scientific images of the 18th century. It shows Benjamin Franklin, the heroic scientist, flying a kite in a storm, proving that lightning is electrical. But although Franklin proposed this experiment, he almost certainly never performed it. more likely is that his most significant experiment was another one, which he proposed but didn't even conduct. In fact, it didn't even happen in America. It took place here in a small village north of Paris called Marly-le-Ville. The French adored Franklin, especially his anti-British politics, and they took it upon themselves to perform his other lightning experiments without him. I've come to the very spot where that experiment took place. In May 1752, Georges-Louis Leclerc, known across France as the Comte de Buffon, and his friend Thomas-Francois Delabarre erected a 40-foot metal pole more than twice as high as this one, held in place by 3 wooden staves just outside Delabarre's house here in Marly-le-Ville. The metal pole rested at the bottom inside an empty wine bottle. Franklin's big idea had been that the long pole would capture the lightning, pass it down the metal rod, and store it in the wine bottle at the base, which worked as a Leyden jar. Then he could confirm what lightning actually was. All his French followers had to do was wait for a storm. And then on May 23rd, the heavens opened. At 12:20, a loud thunderclap was heard as lightning hit the top of the pole. An assistant ran to the bottle. A spark leapt across between the metal and his finger with a loud crack and a sulphurous smell, burning his hand. The spark revealed lightning for what it really was. It was the same as the electricity made by man. It's hard to overestimate the significance of this moment. Nature had been mastered. Not only that, but the wrath of God itself had been brought under the control of mankind. It was a kind of heresy.
Franklin's experiment was very important because it showed that lightning storms produce or are produced by electricity, and that you can bring this electricity down. That electricity is a force of nature that's waiting out there to be tapped.
Next, Franklin turned his rational mind to another question. Why the Leyden jar made the biggest sparks when it was held in the hand? Why didn't all the electricity just drain away? And drawing on his experience as a successful businessman, he saw something no one else had. That, like money in a bank, electricity can be in credit, what he called positive, or debit, negative.
For him, the problem of the Leyden jar is a problem of accountancy. Franklin's idea was every body has around it an electrical atmosphere, and there's a natural amount of electric fluid around each body. If there's too much, we'll call it positive. If there's too little, we'll call it negative. And nature is organized so the positives and the negatives always want to balance out, like an ideal American economy.
Franklin's insight was that electricity was actually just positive charge flowing to cancel out negative charge, and he believed this simple idea could solve the mystery of the Leyden jar. As the jar is charged up, negative electrical charge is poured down the wire and into the water. If the jar rests on an insulator, a small amount builds up in the water. But if instead the jar is held by someone as it's being charged, positive electric charge is sucked up through their body from the ground to the outside of the jar, trying to cancel out the negative charge inside. But but the positive and negative charges are stopped from cancelling out by the glass, which acts as an insulator. So instead, the charge just grows and grows on both sides of the glass. Then, touching the top of the jar with the other hand completes a circuit, allowing the negative charge on the inside to pass through the hand to the positive on the outside, finally cancelling it out. The movement of this charge causes a massive shock, and often a spark. The modern equivalent of the Leyden jar is this, the capacitor, and it's one of the most ubiquitous of electronic components. It's found everywhere. There are a number of smaller ones scattered around on this circuit board from a computer. They help smooth out electrical surges, protecting sensitive components, even in the most modern electric circuit. Solving the mystery of the Leyden jar and recognizing lightning as merely a kind of electricity were two great successes for Franklin and the New Enlightenment movement. But the forces of trade and commerce, which helped fuel the Enlightenment, were about to throw up a new and even more perplexing electrical mystery. A completely new kind of electricity. This is the English Channel. By the 17th and 18th centuries, a good fraction of the world's wealth flowed up this stretch of water from all corners of the British Empire and beyond, on its way to London. Spices from India, sugar from the Caribbean, wheat from America, tea from China. But of course, it wasn't just commerce. New plant and animal specimens from all over the world came flooding into London, including one that particularly fascinated the electricians. Called the torpedo fish, it'd been the stuff of fishermen's tales. Its sting, it was said, was capable of knocking a grown man down. But as the electricians started to investigate the sting, they realised it felt strangely similar to a shock from a Leyden jar. Could its sting actually be an electric shock? At first, many people dismissed the torpedo fish's shock as occult. Some said it was probably just the fish biting. Others that it couldn't be a shock because without a spark, it just wasn't electricity. But for most, this was a very strange and inexplicable new mystery. And it would take one of the oddest yet most brilliant characters in British science to begin to unlock the secrets of the torpedo fish. This is the only picture in existence of the pathologically shy but exceptional Henry Cavendish. Because an artist sketched his coat as it hung on a peg and filled in the face from memory. His family were fantastically rich,
artificially, and to say that that spirit, that living force, that agency was the same as something produced by God, that God had put into a living human body or a frog's body, that seemed sacrilegious to them, because it was eliminating this boundary between God's realm of the divine and the mundane realm of the material.
Spurred on by his religious indignation, Galvani announced a new series railway stations and streets began to be lit from a more powerful source, electric arc lights. The first arc lights were demonstrated by Michael Faraday's mentor, Sir Humphrey Davy, at the Royal Institution as early as 1808, and they worked by passing a continuous spark of electricity across two carbon rods. Under intense white glow was just 2 only very expensive, but was a logistical nightmare, because this was one of the busiest square miles in the world.
Edison chose this area for a reason. Wall Street. Rich, important, influential. Because for Edison's system to make money, all these wealthy customers had to be in a mile from the power station.
And this was because Edison calculated the thickest cable he could afford only carry an adequate amount of this continuous direct current to customers within this range. This was a huge leap forward, because for the first time, dozens of customers could be supplied by just one power station. But there was a big problem. Edison's network could never be economical in lighting America's new suburbs. It just didn't have the concentration of customers needed to make building these expensive power stations worthwhile. Had we stuck with Edison's way of generating and distributing electricity, the world would be a very different place.
We'd have to have power stations scattered around no more than a mile apart, even in the centres of our towns and cities, and it will be extraordinarily expensive to even provide power for smaller communities. But someone who held the answers to these problems was about to enter the story. Someone who would help create the modern world, and would play an integral part in one of the biggest fallouts in scientific history. His name was Nikola Tesla, and he was right under Edison's nose.
Nikola Tesla was a Serbian inventor who was born in Croatia and who worked for Edison briefly after arriving in New York at the age of 28. European, introverted, a deep thinker. Was everything Edison wasn't?
Edison and Tesla could not be more different in the way that they handled their self-appearance and their manners, and the way that they constructed a public image for themselves. Edison cared less about the clothes that he had on, and if he spilled chemicals on his good Sunday suit, then he spilled chemicals on his good Sunday suit. He was, basically a very, very kind of slovenly guy. Tesla, on the other hand, even as a young man in his mid-20s, is thinking about his appearance, how he comes across to people. So he cares about his clothes, he cares about his manner, he cares about how his photograph, his portraits are taken, and he always wants to make sure that he has a nice three-quarter profile. They don't see the fact that he has a bit of a pointy chin.
The life and death of Nikola Tesla is one of the most fascinating yet tragic stories of scientific brilliance, cutthroat business, and shocking public relations stunts. The American public may have been wowed by Edison's new direct current power stations, but Tesla was less impressed. He had a dream. Electricity could be transmitted across entire cities, even nations, and he believed he knew how it could be done, by using a different type of electric current. Electrical experts knew that the smaller the current sent down a cable, the smaller the losses in electroresistance, so the longer the cable could be. Tesla proposed using a method of transmitting electricity where the current could be lowered without a fall in the amount of electrical power at the other end. It was called alternating current. Alternating current, exactly. It's electric current that alternates between moving in one direction, then the opposite direction very quickly, as opposed to a direct current which moves only in one direction.
Tesla was interested in alternating current because, like other electrical engineers in the late 1880s, he realized that as you raise